Broadly, first week, today we are going to cover basics of basics of elements, power, voltage, current, voltage sources, current sources. What are those properties? This is week one. Plus, we'll do a lot of problem solving. So every Monday after the class, I will give an assignment, anywhere between 8 to 10 problems, roughly. And this is something that you will work out and then you will upload before end of Friday. Okay? Because on Saturday, we will have in the lab, in the tutorial class, right? We are going to solve these questions. We will solve these questions, and that should help you to compare and analyze, go about problem solving. Because the thing about all this circuit analysis is about solving problems. If you feel confident in solving problems, your concepts are well, right? Then I'm sure you're going to do well also in subsequent courses. Okay, so that's how we're going to do. Monday class followed by an assignment problems, and you will have time till end of the week to finish those assignment. Saturday we're going to discuss the assignments in detail. So I will solve those those questions. And Thursday class we will also work a little more advanced concepts on what we cover on Monday, followed by a few more questions. So you will have each class, there's going to be a few questions at the end of the class, which you will then solve and submit by end of Friday. Okay. And Saturday, we will solve those questions. And following Monday, we will go with a new topic and then go on. So this is how we will structure the course. So Monday, Thursday, lectures, followed by problems. And Saturday, we will solve some of those problems. So it depends on the time, how much we can cover, but at least we will make sure that the concepts are all clear on these problems, so that you feel confident attempting to solve those problems. Okay, so this is the structure we will have for 5 weeks. Week one is going to be unfortunately I've missed that slide set here, but I will make sure I will add that and then upload it. So week one is going to be basics of voltage sources, power sources this week, and with some problems, load, source, current, what is the power, and then so on, right? Then week two, we will talk about Kirchhoff's current law, Kirchhoff's voltage law, superposition principle. How do you analyze complex circuits with resistors and capacitors in place, or basic resistor network, and so on. Week three, we will talk about elements. Go into active elements like capacitors, resistors, capacitors, and inductors. How do you analyze circuits with these elements? Capacitors, resistors, diode, inductors, and so on. Week 4 and week 5, we will focus on op-amps. Okay? So op-amp based circuits, properties of op-amp, how do you analyze it? And each class there will be more problem solving, because I understood the feedback from you is you want to solve a lot more problems, right? And more tutorials, more exercises. So request all of you to really put in that effort to do the sums or the exercises, and so this should help you be prepared well for the tutorial on Saturday. Okay. Last but not the least, end of every lecture, while you're listening to the lecture, please keep a rough work or a rough notes or a white paper ready with you, and make your notes. Make your notes on the key points, whatever you've understood or whatever you're taking. Have a pen and paper with you. And what I want you to do is at the end of the class, make sure you're uploading your running notes. Take a photograph and upload your running notes in the LMS. Okay. Let me quickly show where to upload in your LMS. Right. Let me show you. So if you.
The screen is not shared.
Yeah. Trying to open it. So are you seeing my screen?
Yes, sir.
Yes, sir.
So zero to silicon, as soon as you go there, right, you click on assignments, it just pops up here, and here you just click on this and submit your running notes. Okay. So for today's class, you need to submit notes here. So for Thursday, it's here, and then Saturday, it's here. So basically have your running notes. As soon as you're done, I need you to submit the running notes before 9 p.m. Okay. And whatever, note the key points, whatever you liked or whatever you didn't understand, this also two things that will help. One, it will help me understand who is involved and then who is paying attention, and it will also tells me also who got the concept right and who got the concept wrong. I'll quickly just scan through your notes. So that just helps you to be more engaged and keep noting these lectures, right? And at the end of the lecture, it will be until 8:30, and between 8:30 and 9, please take a snapshot, take a photo, upload them here, upload your notes, okay, as one file. Okay, so those are some things that we want to talk about. Any questions before I move on? Any questions? Anything? Any comments? Any questions? Are we good?
Sir, question is,
Yeah.
sir, can you also teach audio circuits?
When you say audio circuits, you're talking about power amplifiers and things like that.
Yes, sir.
That will be a bit too specific because we'll cover the amplifier circuits, and maybe while I'm covering op amp, right? Let me see. It's power amplifier circuits are nothing but you are driving a very low output impedance, like your audio. You have a few ohms, right? And you need a very
Because
very
sir,
high.
basically there's component circuits used in communication also, no?
As an example, can you give me an example of which circuit you're
An
interested?
amplifier or
Yeah, so we'll talk about amplifiers. The op amp in the op amps, we will talk about
Yes, sir.
amplifiers only. The
Yes, sir.
2 weeks we will talk about amplifiers.
So like just speakers or any
Correct.
other.
So
We can
this speakers.
defense also, sir. Audio instruments are there, optical radars or something
No, I
like
think that is way beyond the scope of this current. So we'll talk about amplifiers, we'll talk
Okay,
about the
sir.
load
Okay.
and then
Okay,
fundamental.
sir.
Because
Okay.
this we need to keep it general, because this is like the time of everybody is here. Everybody needs to be we'll touch upon the common topics, and I will make sure that in one of the lectures I will ensure that the high output power circuits are talked about, which is basically your amplifiers that typically drive your speakers and then so on, right? I will touch upon that.
Yes.
Okay.
Yes, sir. Yes, sir.
So let me make a note. I'll keep this in mind. We'll touch upon that. But it will be kept very brief so that it's useful, and that's why we call this a zero to silicon, right? So it is
Yes, sir.
basically some course that is, I mean, it should be useful for people to start from fundamentals and then build on it,
Yes.
right? That's why we call it zero to silicon. So
Yes.
again,
Sir, recently the Indian government had said 4 plants are installed in the India. One is Punjab and 2 Odisha, and one is I think Bhubaneswar also, and I don't know.
one is Bhubaneswar,
The
one is Andhra
silicon
Pradesh.
carbide, he said.
Yeah, that's in Bhubaneswar.
He said how you just also cover this topic in this.
No. That's
Okay,
all. I
okay.
think for that we will talk about
This is the last
some.
after partner, I think.
Actually, these things like power semiconductors we will deal in the specialization semester.
Okay.
In the thing, right? And
Okay.
we could talk about, if you pick analog design as specialization, some of these can be talked about in the other course. But this is more, I would say, again, want to set the expectations clearly. This is the fundamental course, a foundation course where
Okay.
we are trying to refresh the basics. That's why we call it a zero to silicon. And
Okay.
power
Okay.
semiconductors, gallium nitride, silicon carbide, the technology and how you use it. This is completely advanced stuff beyond the scope of this course. Okay? But we will separately talk about it. I'm sure I understand your interest in learning about that,
Yes,
and
sir.
also I'm always happy to discuss. But the
But
scope
sir,
of this,
I just know a little bit, but if I go to that deep in knowledge, so I
yeah,
just
this is
ask the
not
question.
correct. So but this course is not meant to talk about power
Yes, sir.
semiconductors.
I understand that. Yes, sir.
Yeah, but having said that, whatever we are talking about in this, right, output impedance or all the things that we learn, they are relevant to anything. Pick anything.
Okay.
This is relevant.
Okay.
Okay.
Okay, sir.
Okay. Okay. Good. Thanks. Thanks for this this comment and so on. So
Thank you,
any
sir.
other? Sure. Any other comments? Priyanshu, Kavya, Shreya, Sri. I still don't see the cameras turned on. Avan Kumar. So any comments?
Sir, I'm excited.
Yeah.
Okay. Looking forward. Wonderful. So let's learn together. I mean, it's again, there are always some things that you can challenge me on this, right? And this concept, something is not learning, and in that process, I'll also learn. Let's learn together. Okay, let's get started. Let's talk about this. Where is it? Duplicate slide view. Okay, good. Yeah. Okay, so let's start. Fundamental electronic components. So these are list of things that we all hear, basic stuff. And somehow all of what we do fundamentally are correlated to this. So first set of things are related to, basic elements like, resistor, capacitor, inductors or inductive component. So resistors are passive elements because they don't store energy. They just dissipate energy, right? That's why they are passive. So they react but they don't need any power to operate. This means, resistor does not need something to turn on and then work. Okay? It's a passive component and it just dissipates. So resistance and every circuit in the world, right? A wire, starting from a wire to most complicated processors, always have a resistor and capacitor. Any wire, any metal line, any wire, anything will always have a resistor and a capacitor. Okay? So then you have so capacitors, these capacitors store energy. These are active elements. Okay. So if you think of, so this is typically, if you talk about this, right, these are passive elements. Resistors are passive elements or typically lossy elements. Okay. Capacitors are also passives, right? But they store energy. Passive, but they store energy. So they are storage elements, right? And a very big capacitor is a battery. The battery is also like a capacitor. Whatever we use in our cars, everything, right? It's also a form of a capacitor. Okay. Now, inductors also are passive elements, but they store magnetic energy. Okay. Capacitors directly store electrical energy, but inductors store magnetic energy, right? And this gets converted into a voltage or a current by a certain relation, flux, magnetic flux into your and that magnetic flux or magnetic energy is now converted. In the job of inductor is to convert that into electrical energy. Okay. Now there is a new term called memristors. So how many of you are familiar with memristors? Have you heard about this term? Okay. So I want you to take this as an exercise. Just read about memristor. Okay? Memristor as an element. So this is called the famous fourth fundamental element. Okay, so we are all familiar with the resistor, capacitor, and inductor, and they have these unique properties. But these memristors are now playing a very big role in memories, in neuromorphic computing, and so on. So think of this like resistors with a memory. That's why they're called memristors, right? So normally your resistors, they are instantaneous. You have to apply a voltage across a resistor, you get a certain current, and V by I is your resistance. But imagine you have a resistor which has some memory. So whose present resistance is a function of the previous voltage that is applied. Okay.
Excuse me, sir.
Yeah. Yes, Shivam.
Can you briefly explain what is neuromorphic computing?
So neuromorphic is brain related. So there are, see, when you want to build intelligent circuits, right? You are trying to mimic how a brain works. Brain has some neurons, there is a synapse, and whenever an electrical signal that comes, right, then that gets transferred and gets stored, and it's very, so understanding how brain works is a very fascinating topic because you can now start building very complex mechanism. I mean, just imagine how a multiplication happens in a brain, right? I mean, we know how multiplication happens in a digital circuit, right? You have X, you have Y, and then you have some digits, and then you do a multiplier. So shift, carry, adder, all this. These are fundamental lists. But high computational things, all of these come with a certain energy budget. And the lowest budget, most complicated processor ever built is your human brain. It doesn't go with your conventional look ahead, carry, put this, multiply this, and it doesn't work that way. There's a way that it works, and people have been studying this, studying how to build a processor which can mimic brain, right? That's where you call it as a neuromorphic computing. Okay, and even for neuromorphic computing or memories, advanced memories, these memristors are a very interesting element. So these are resistors whose resistance is a function of previous voltage. Let's say you applied a voltage some time back, right? And because of that voltage that you applied, there is a resistance that happened. And now that stays, even if you remove the voltage, right? That stays, that resistor stays as is. If you apply a different voltage, the resistor will now change accordingly. So think of this like a resistors with a memory. This is called a fourth fundamental element invented by Chua, CHUA in 1970s. And these memristors play a very, very important role now in all your emerging memories, emerging memory design. Those of you who are interested, it's a very nice, it's a beautiful combination of how semiconductor compound, how your materials, semiconductor materials are used to build such an element, right? This is called a fourth missing element. Read through it, very fascinating topic. Okay, and then of course you have, so these are all elements which have certain properties, and then you have this power sources. You have voltage, you apply a voltage, you apply a current, right? So there are voltage sources and there are current sources. Then comes the active or or non-linear, a bit of a non-linear components. First one being a diode. So this is basically a valve, like a diode is able to, it's like a gate, right? You can open the gate, you can close the gate, you can allow a signal to pass through, or you can block a signal to pass through. This is quite powerful. So diodes do this job. And then you have whole bunch of transistors, JFETs, MOSFETs, bipolar, all of these are active elements. So this means, what is the definition between a passive and an active element? Anybody? What is an active element? What is an active element and what is a passive element? Anyone, take a guess. It's okay. I mean, you don't need to be right or wrong. That's okay. Take a guess. When do we call something as a passive element? When do you call an active element? Right?
So active and passive would be like, depending and non-depending, sir.
Okay, depending and non-depending. Okay. Who else? Who else wants to talk about it?
Element means loads. That means power is
Active
needed in
element.
circuit like that.
Okay.
Active elements means it's a like batteries. Power is generating.
Okay. So one way to classify it easily is to see active elements work when you have power. Okay. Passive elements actually do the job. So for example, think of a MOSFET, right? You have to apply a certain voltage, put your MOSFET in some configuration to make it work, right? Whereas a resistor, right? Apply a voltage, you get current. Apply whatever voltage you apply, even if you apply 1 microvolt voltage, you get whatever the proportional current. Put 1 nanovolt, you get a proportional current. Put 1 volt, you get the proportional current. Whereas for a transistor, you have to first turn on the transistor, bias it, put it in a region of operation that you want, and then it will start working. Okay. Similarly, op-amp, which is a operational amplifier, this is a very, very fundamental component for circuits, right? Now, for several years and even now, this is like the like the bread and butter of any circuit designer, understanding op-amps. So initially, people used to just have these general purpose op-amps, as an example, LM741 and so on. So people have already designed these op-amps, they are available as ICs. Now you use the op-amps to build circuits around it. Put most times these components allow you to put a feedback resistor or a capacitor, make a filter or make some amplifier and then so on. So this They used to allow it. But what happened over the years is that, each application needs a different flavor of op-amp. Okay? And in fact, I did mention in the previous launchpad that, a simple two-stage amplifier can be designed in 4,000 different ways. You may be surprised that literally a simple two-stage operational amplifier, there are multiple ways of doing it. Literally, there are, if you do all the permutation combination there are 4,000 ways of designing an op-amp, okay? And many ways. So input pair, compensation, what load, what is the output stage, what is your input stage, which is the dominant pole compensation, which is your load. All of these will matter, and then each op-amp is different, and that's why people have moved from using standalone op-amps to actually designing custom op-amps for your application. Which means whenever you have an application, you design the transistor level circuit directly and just do or design circuits whichever you will meet your requirements just with the enough power and area budget. Okay, but op-amps is one of the fundamental components which you need to learn, and any analog design interview or any circuit design interview, any circuit design interview, people will ask you about op-amps, and if you don't know about op-amps, right, that's kind of a big setback. So understanding op-amps, understanding the concepts using op-amps is extremely important for any circuit designer or any electronics engineer. Okay, so keep this in mind, and that's why we will focus, I think, roughly around 6 lectures completely on studying op-amps, understanding op-amps, fundamental properties, review all these op-amp based circuits. Okay, then of course the logic gates. The logic gates are a combination of MOSFETs, all your digital logic, AND, OR, XOR, blah blah blah. And then eventually you have flip-flops, D flip-flop, SR flip-flop, your latch, and then so on. So all of these are again a set of active components which work only when you have power supply. Then you have more complex components which are ICs, which is a combination of several of these resistors, capacitor, diodes. So some of these combinations are given as an IC. As an example, an oscillator IC, LM555, right? A timer IC. Okay, this is a standard, very famous IC, LM555. So this is built using a combination of transistors, resistors, capacitors, and maybe a comparator, maybe an op-amp. Similarly, you have PLCs, there are sensors, and so on. So all of these electronic components as a combination work, and then a smart designer understands what to use where, understands the limitations of all of these, understands how to make things work. Okay, and that's what we will focus on right now. Okay, right. So let's just quickly glance through what are the properties of these electronic components. Okay, first let's go step by step. Okay, and this is very important. First, resistors, we all know about it, right? It's basically used to control voltage and current in an electrical circuit. Right? So a resistance simply means how much, say, think of Newton's first law of motion, right? Or a law of inertia. A body tries to be in the state of rest until a force is acted upon it, right? So anything that you want to apply or you want to move tries to oppose the motion, and this opposition is the resistance. Similarly, whenever there is a circuit, even the circuit or these resistor element tries to oppose the flow of current. Okay, so and that opposition to the flow of current is basically your resistance. So first, larger the resistance, okay, larger the resistance, smaller is your current, because it's not allowing the current to, it's opposing the current, right? So it makes the current smaller, and this is, and resistors again are, you can build resistors in, let's say, 20 different ways. There are surface resistors, there are integrated resistors, there are NTCs, there are thermistors, right? Different resistors, and these are very powerful, because they usually they are governed by a simple Ohm's law, where they say R is equal to V by I. So resistance is the voltage. So what is V? V is the voltage across the terminals. right? Keep in mind, whatever is the voltage across the terminals, that divided by the current flowing through the resistor or flowing through the element is your value of resistor. Now, there are instantaneous values. For example, if you have a fixed resistor, then this equation V by I, you can even apply an instantaneous equation here and this will still be valid. So this means at any point of time, if you have a voltage, a varying signal, right, some signal that is varying with time, the current that gets generated will also vary exactly in the same phase. V of t and I of t will maintain a fixed ratio always and always if you have a passive linear resistor. What also happens normally is that this resistor, practical resistors are, so R is a function of voltage across the resistor. It is a function of temperature across the resistor. Okay, the resistor is not fixed. Of course, we think it is fixed, but the resistors are also a function of voltage. See, so you can see that in this equation, this equation is supposed to be a linear equation, right? So if you think of it, V of t is R into I of t, correct? Let's first erase the slide. So I'm going to write on the top. So V of t, whatever is the voltage, this is R of R into I of t. So if you, so can somebody tell me if I want to draw a transfer characteristic, right? So as an electronics engineer, math analysis is very important because a math analysis helps us to understand how the circuit is behaving. Your fundamental math analysis is very important. So whenever you are asked to draw transfer characteristics, right? What is the definition of a transfer characteristic? Okay, anyone, if you're asked to draw a transfer, what is a transfer characteristics? In mathematical terms, they call it HFS, or the gain or whatever, all of these, right? Transfer function. What is a transfer function? It is simply the ratio of output to your input. That's all. Very simple. So remember, a transfer function or transfer characteristics, it just means your output divided by your input. So it is a behavior or a description of how your output changes when you change your input. Mathematical terms, this is also called as a gain. This is also called as a slope. All of these are different names for this transfer function, slope, whichever way you call it, right? Ultimately, it is output by input. Now, for a resistor, if I want to draw a graph, if I want to draw a mathematical representation, let me know what should be my x-axis if I have to plot the transfer characteristics of a resistor. What should be my x-axis? What do I choose on my x-axis?
So slope we have also be calculated.
Right. So I need to plot the transfer characteristics of a resistor. Somebody asked you, say, please plot the transfer characteristics of a resistor. Right. This was the question that you asked. So you have to draw obviously transfer characteristic means there is an input, there is an output, right? You are now drawing a graph between input and output.
Voltage will be the input, output will be current.
Okay, and why not the other way around?
Because when you're applying the voltage, the resistor is nothing but how much current is opposing, right? So
okay,
outcome should be in terms of current. Might be.
And how about the other way around? If you force a current into the resistor, it will generate a voltage across resistor, right?
Okay.
That is also true. If you had a current source, you are right. I mean, it depends on what you are forcing, what is your outcome. It can be a voltage force and current is your outcome, current is your output, right? Or it can be a current input and a voltage output. So when somebody asks you to draw transfer characteristics, right, you can pick whatever value of that in your x-axis. So it could be either I or V on x-axis, and on y-axis you will have V or I. Both are equally correct, right? Because if you force a current, you get an output voltage, then it is an I in versus V out. Okay. Now, if you force a voltage across this and you get a current, it is V in versus I out. Okay. Now, let's take one example where I will say, let's just take V by I. Okay. So you are forcing a current and you get an output. So it is an I in versus V out. Okay. Now, for a simple resistor, given that V is equal to IR, what is my transfer characteristics? Okay. Somebody help me with this. Who can help me? Who can start? How do I draw transfer characteristics?
Sir, for that we should have the V out and V in should be known, sir.
V out, and so here it is V out and I in, right? I'm taking current as my input, and
okay,
output is my voltage, because I know that V is equal to IR, right? So my fundamental equation here is V is equal to I into R. So this I know it. Okay, so whatever be my current input, I in, the voltage output is going to be I in into R. Simple. So simple Ohm's law. V is equal to IR. Now, the reason why I'm asking you this, because we all know Ohm's law, but somehow we get scared or confused when somebody quickly asks you, okay, draw the transfer characteristics of Ohm's law of this, right? So somehow we are, our brain is not tuned to this, what do you mean by transfer characteristics? It's nothing, very, very simple, right? You are asking what is I in. If you apply an I in, you apply an I out. Look, so let's start from fundamental principles, right? Whenever you are asked to draw transfer characteristics, first think, start from origin. Okay. When my current input is 0, what is my voltage output?
0.
0. Right? So you got your first point. What is it? This means for a resistor, you should include origin in the graph, because when current is 0, input is 0, output should be 0. Right? Now, what is the other point? When you have some current, let's say you have 1 milliampere as an example, then you will have some voltage here, corresponding voltage. You have twice the input, you will have twice the output, right? So now which other points you have? You've got this point, you have another point here, and so on, right? So this is my transfer characteristics. So do you agree?
Yes,
You agree
sir.
with this? Slope of this line obviously is the resistor, right? Now, if you leave it here, then you have done only half. This answer is only half correct.
We have constant as well, or
which constant?
The resistor is constant, sir. Yeah.
Correct, and that's why the slope is, that's why it's a straight line.
Yes, sir.
Right? Because resistor is constant, this means slope is constant, so you get a straight line, right? I am
Yes, sir.
saying this graph is only half complete.
Line passing through the origin.
Yes, it is passing through
Complete
origin.
straight line. Downward also.
Ah, very good. Very good. So, what if you have a negative current? What happens if you have negative current? And what does negative current simply mean? It's just current in opposite direction. That's all. Negative current or negative voltage simply means that it is going in an opposite direction. The direction is changed, and that the change of direction is represented as a negative sign. Keep in mind, there's physically it is the same. There is nothing like a negative current. In reality, there's nothing like a negative current. It just means that the current is now going in an opposite direction. Absolutely, right? So you should draw the graph also on the bottom side.
Yes.
Okay, so when the current goes in opposite direction, then the voltage convention changes. Right? So it's a negative voltage for a negative current. It just means that the current is in opposite direction, so the voltage built will be also in opposite direction. That's all it means, right? This is the transfer characteristics of a resistor. Okay, and believe me, interviews ask this. It looks very, very simple for us. Oh, Ohm's law, there is absolutely nothing, but people struggle drawing a basic transfer characteristics also, simply because somehow we are not tuned to mathematically representing something. So whenever So rule number one or takeaway from this is, whenever you are asked to draw any transfer characteristics, start from so first point is what happens when input is 0, x-axis is 0. Now analyze, think, start with that. What happens? Sometimes you need to go, what happens when my time is infinity? As an example, right? You are asked to draw some circuit where, and I'm going to use this also, right? Sometimes you are asked to draw voltage as a function of time, right? V of t, and the x-axis is time. Okay. Now, same thing. What happens at time t equal to 0? What happens at time t equal to infinity? What happens at time t equal to minus infinity? So this analysis you start, right? Then you know the endpoints. You know where to start, you know where to end, and now you can briefly sketch, think through and then sketch something. So this is, even if you don't get accurately right, at least people will start appreciating that you are analyzing it correctly. So keep it in mind whenever you are asked to draw any transfer characteristics, whatever be it, diode, MOSFET, whatever be it, right? Keep in mind what happens at V equal to 0 or I equal to 0 or T equal to 0, my initial condition. So when my input is 0, input is maximum, input is minimum, at least get the boundary conditions and then go further. Okay. So resistor wise, very cheap component, very available, and then take any board, remove any component in any electronics board, right? You cannot build components without resistors. Resistors used in filters, resistors are used in amplifiers. Many cases they are used in current limiting. This is nothing but a fuse. It's basically, resistor is also like a fuse where, so our fuse that we have, right, in our in our electric meters there in our power fuse. What does it have? You use the property of resistor's temperature coefficient there. Basically, resistor produces a heat, right? What is the heat? Whenever you have a current, the heat or the power, whatever is heat produced, is I square into R. Okay, this is nothing but V square by R. So I is equal to V by R. So let's call it this way. I is equal to V by R. So power is V square by R, right? So V square by R square into R, it's basically V square by R. So either you call it as V square by R or I square R. This is the power that is dissipated. Now, whenever you dissipate power in a resistor, it dissipates as a heat. Things become hotter. What does the power dissipation mean? Loss of energy, right? And how does the energy gets lost? You lose energy because the energy is getting dissipated as heat. Okay. So, and whenever the energy gets dissipated as heat, now the resistor temperature coefficient increases, or the resistor somehow changes its value, and suddenly whenever there is an appliance short in some room, maybe the switch is getting short or your bulb is getting short somewhere, right? Now what happens when things getting short, positive or negative become short, right? You see a huge current, and whenever there is huge current, the I square R increases, so the tempo of it increases, and suddenly the fuse just disconnects itself to prevent your appliance. So a very simple fundamental property of a resistor is really protecting our homes as a fuse. This is what happens. Energy lost, I square R, we are using it. I square R loss, we use this property to really disconnect the circuits, disconnect your appliances. This is what happens in your fuse. And it's a special material whose tempo can be controlled, right? Okay, and resistors do not store energy. It's like, it's a resistor, that's why they don't call resistor as a bank. So this is like somebody who, whenever you put something in the bank, they spend it, right? Resistor will not save anything in the bank. Whatever money we have, somebody just spend it, right? No, they don't save anything. So resistor always dissipates energy. It doesn't store energy. Okay. Capacitor is exactly opposite. Capacitor is nice, so it stores electrical energy. And the only way capacitor can discharge is when you connect a resistor. The only way the capacitor will start discharging energy, the stored energy gets discharged is when you have a resistor or resistance in series, then it discharges. Otherwise, capacitor is lossless. By default, a capacitor is lossless element. Okay? And the amount of energy stored is dependent on the, or amount of charge or amount of energy stored is dependent on the capacitor value. Larger the capacitor, larger is the charge you can store. And equation is charge stored is equal to value of capacitance into voltage. Okay. Now, one question in this, right? Sometimes, so let's just understand the concept of at this point, right? I want you to understand the concept of linearity. I mean, we keep using the term linear circuits, non-linear circuits, right? What is the definition of linearity? When do you call something linear? And very important point, because you want to, most times the circuits, you want to linearize your circuits, right? You want to operate in linear region. Why? Linearity simply means that if an input x1 gives you y1 output, so you have an input which is x1 and this gives you y1 as your output, right? And you apply another input x2, so and x2 can be a voltage or x2 can be a current, right? And if this gives you y2 as your output, then x1 plus x2 should and must give y1 plus y2.
Plus what?
Yep. Right. So this is the and this is the fundamental basis for your superposition principle or whatever. So circuits are linear. So if one input, some input is giving, a certain current is giving you, let's say 1 milliamp gives you 1 volt, right? 2 milliamp gives you 2 volts. Then 1 plus 2, 3 milliamp should give you 3 volt. 1 plus 2, so inputs and outputs. So this is why it is called as linear. Okay, and this is the fundamental principle of linearity. When you have two independent inputs, each giving rise to the respective outputs, the sum of these inputs should give rise to a sum of the output. Similarly, a difference of the output should give rise to difference of the output. Mathematically, okay, so and that's why every time we talk about circuits, we also need to build our mathematical intuition. Mathematically, linear systems are represented as y is equal to mx, where x is your input, y is your output. Of course, you can have an intercept, which is c, right? It's a constant, right? The easiest way to draw is this is your x. So if you have an interrupt, so who can draw this? Let's draw this equation. You are given an equation y is equal to mx plus c, right? Draw the transfer characteristics of this. So
We cannot draw, sir.
Right line.
Why? Why?
Sir, because we are having a constant c.
Okay, but how do I identify this c? Go with your first principle. What was the first thing that we said?
At x is equal to 0.
Absolutely. X is equal to 0. So at x is equal to 0, what is the value of y?
It's a constant.
C, constant. So call it as constant. See, this can be anything. Maybe it is positive constant, it is negative constant. That's fine. We don't know that, right? Let's call it C here, right? Now, if x is increasing, what happens to y? It starts from this point, right? It goes up. Correct?
Yes,
If C was negative, then you basically start here and then you go up.
negative x.
If C is 0, you start from origin, you go up, right? Anything, you should be able to just go with the fundamentals and then draw it. And the slope of this is m. The slope, or in trigonometry terms, does somebody remember what is the slope of a line? If you have an angle theta.
Tan theta.
Tan theta.
Tan
Very good.
theta.
Tan theta. Right? What is okay? And why is it tan theta? Let's also
It's a
ask
sin
that.
x.
So let's say you have a line like this, right? Why is tan theta a slope? If you have an angle theta, what is tan theta? Height by
Opposite side by
opposite side by
Perpendicular by b.
adjacent side.
Very good. So what is height here? Height is y-axis, right? Width
by
is x-axis. X-axis. So tan theta is nothing but y by x, and this is your slope, right? So you can beautifully correlate your calculus, your trigonometry, your Ohm's law, everything. So if you draw an equation of voltage by current, your tan theta is this, right? And this is how we are computing the impedance now, right? Tan of this line is your impedance. Okay. So similarly, you can have capacitance or Q charge, which is capacitance into your voltage. Keep in mind, practically there may be capacitor which are a function of voltage itself. Okay, these are non-linear capacitors. Typically, MOSFET capacitors are non-linear. So normally we talk about Q is equal to CV. The assumption is that C is independent of your voltage, right? That is our normal assumption, that C is constant. So if Q changes, then V will change, or if V changes, Q will change with the same proportionality. This is the ideal world. Practical world, there are some capacitors where the capacitance itself is a function of voltage. This is a non-linear capacitor. Okay. Now, since we're talking about non-linearity, how do we represent non-linearity? What is a non-linear system?
MC squared.
Y is equal to, let's call it f of x. If x is your input rate, what is the mathematical representation of a nonlinear signal?
Plus.
No, nonlinear system. See, y is equal to mx or y is equal to ax plus c, right? That is your linear system. So you had only one proportionality term, x power 1. X power 1, when exponent is only 1, let me write it down other way around. So linear system is y is equal to a naught plus a1x. In other words, this is what we were saying, c plus mx, right? Y is equal to mx plus c. So c is your constant, this is your a naught. Mx is your slope, and that is your a1x. This is your linear element. What is a non-linear element? A naught plus a1x plus a2x square plus a3x cube, so on, so on, so on, right? And this is nothing but mathematically, this is a Taylor series expansion. This is called as Taylor series expansion of any f of x. F of x is f naught 0 plus f dash x, f double dash x by 2 factorial. This is that nothing but this. Okay, it is a non-linear representation of a signal. So whenever you talk about non-linear systems, right, the easiest way to represent mathematically is this. Okay, and now let's apply the same rule. I know I'm showing something and talking something else, but since we are in this linear region, let's just refresh all our concepts. Okay, so what did we say about linear systems? You had one input, and let's say you had x1 input and you had x2 input. X1 plus x2 should give you y1 plus y2, right? Let's apply the same concept here. If you had f of x1, you have x1, then x1 square, then x1 cube, so on. If you had f of x2, right, then you would have same thing, a naught plus a1 x2 plus a2 x2 square, and then so on, right? Now what is f of x1 plus x2? Okay, until this point this is okay, but now you see that for a2 you get a2 x2 plus x1 whole square, right? Now what is a plus b whole square? A square plus b square plus 2ab, correct? So this is nothing but a2 x2 square plus a2 x1 square plus 2 into x1 into x2. So that is an extra term that we are getting. So it is, so that's why this is not f of x1 plus f of x2. So the system is non-linear simply because when you take two inputs, the individual outputs of them do not add. So if you add the two inputs, you won't get the addition of two outputs. Okay, so that's why this is called a non-linear system. Most times, this is, you kind of limit it to either a second order or third order nonlinearity. X cube is kind of more than enough. And so Jaskaran, when you're talking about power amplifiers, right? You talk about linearity of these power amplifiers, linearity of your audio amplifier, and this is how the linearity is also modeled. आपका third order harmonic or second order harmonic जो भी आता है इसमें, the harmonic distortion, this is nothing but this. Okay. Now let's go one step further on this nonlinearity, and let's see this math is so powerful because it helps us to intuitively understand the physical phenomena. Okay. Let's, if x is a of sine theta or sine omega t, let's call it sine theta, let's say, right? Sine theta, right? What is sine theta square? What is sine theta whole square?
Sine square theta.
That is the same. Sine theta square and sine square is same, right? It is basically, you get a function of 2 theta there. I think 1 minus cos 2 theta or something by 2, right? So whenever you have theta and you're doing a square of it, you get 2 times the theta. Similarly, when you have sine theta cube, right, you basically get 3 theta. So imagine you replace theta with omega t. Omega is your frequency and t is your time. So when you have a frequency like sine of f, right? If you replace this with an ft, let's replace this with this is ft or omega t, omega naught t. You get 2 times your frequency. This is ft whole square or whole cube, you get 3 times your frequency. So this is your harmonics. You are giving one frequency at your input, but you will get twice the frequency, 3 times the frequency, 4 times, 5 times, 10 times, 100 times the frequency. All these harmonics come. So the problem with the non-linearity of the circuits is that if you give one frequency, a core fundamental frequency, one tone, right, it will generate 100 different tones of all the frequencies, all the harmonics. Okay, that is the problem with, which is nothing but your distortion. Okay, you expect, let's say, for a nice audio amplifier, right, you give a 1 kilohertz sine wave, and as you keep increasing the amplitude, right, you keep increasing the audio amplifier, increase it. At some point, you will keep hearing a screeching noise, and that is because the sine wave got distorted now. It got clamped and it generated many frequencies. Okay. So just reviewing it's not a trigonometry class, but then these are important to know, that linearity, harmonics, all of these come in as an undercurrent. It's important to understand all of these concepts while we are learning about circuits. Okay. So next, inductor, same thing. It stores electrical energy. All your transformers, stabilizing voltage. The voltage is very important because inductor does not allow the current to change instantaneously. Capacitor does not allow voltage to change instantaneously. We learned about it. Capacitor is lazy to change its voltage. Lazy to voltage change. Okay. Inductor is lazy to current change. And we will talk about it. We will talk about it in detail in third class, right? Third week. And very powerful. Inductors are very powerful in all the high current applications because they don't allow the current to spike whenever you have a short circuit. This having this inductor means that your current will still be limited, right? So these inductors or transformers are very powerful. Okay, but They are bulky components. They have weight. So typically these are used sparingly and only when you need it. Okay? A special condition of an inductor is a transformer, where you can now provide an electrical isolation between input and output. So you're not electrically shorting it. You are coupling it through a magnetic flux. So whatever is the change in the input somehow gets in the output. And why? And where is this used? Where is it used? Where a transformer is used in our daily life?
Current power stations.
Power stations. Why? The power stations, the transmission happens in tens and thousands of volts.
The transformer is a static device, no? It is step up or step down the voltage.
Correct. And this is very important because the power line transmission, right? The high, it's a very high voltage. It's in tens of kilovolts and sometimes even 100 kilovolt, right? Now any mishap there, directly imagine if we get somehow 100 kilovolts directly into our house, right? And then it can be absolute hazardous. It can really burn down everything. That is why there is a lot of protection, the transformers, then the redundancies, everything, very high power transformers, which will step down this tens of thousands of volts to give us about 220 volt for our appliances, right? So fundamental, the transformers isolate all our appliances from this 10,000, thousands and hundreds of volts, and then bring us only the 220 volt necessary by a step down or step up. Okay, then we have transistors. Transistors act as the interesting thing about transistors is that transistor can act as a resistor. Transistor can act as a capacitor. You can make transistor act like an inductance. Also, you can make transistor act like a switch. So, and that is the art of using transistors to design circuits. You can actually use transistors in many different ways. So they are key components in amplifiers, filters, data converters, whatever. So transistors, MOSFET technology, JFETs, bipolar technology, silicon carbide, SOI, all of them are somehow, they're semiconductor junction devices. Then comes your integrated circuits. So this is a combination of multiple electronic components, a combination of transistors, inductor, capacitors, resistors, all put in very tiny chip to perform a specific function. Okay, because they are so tiny, they help in reducing the form factor, but they are more complex to debug. So they can't be put on a breadboard. You don't physically see them. Right? That's the problem with IC. The challenge is that you don't see these components. You have to only imagine the circuit, debug, and find ways to make it work. Right? Then the last but not the least, it's the diode, which is also quite powerful and is extensively used in power electronics. Okay? Diode allows current only in one direction. It's a valve, basically like a gate of a dam. You only when it is open, the water flows. When it is on, the water flows. When it is off, it stops the flow of current. Right. So this is used to rectify AC to DC voltage, and it can also be used to protect the circuits from reverse voltage. Right. So a combination of all of these is what is used to now build your circuits. Okay. Ultimately, it is any circuit is now a combination of one or two or multiple of these. Right. So these are the properties of the electronic components. Okay. Right. So let's move on. So practical application. Let's start with one application that is, so let's say your car is not starting. Okay. And you realize you don't know whether it's the battery discharged or not. You turn on the light and you see the headlight and suddenly see that the lights are very dim. It indicates that you have a weak battery. And what is the next thing you do? You borrow your friend's car and somehow get your jumper cables there and turn on the other car, and let's hope this good battery charges your weak battery. Right? So what is the so when you have a weak battery and you have a good battery, right? What is happening to this? What is this good battery doing to the weak battery when you're charging, when you want to charge? What does this do? It is sending some charge, or It is, you can think of a charge in a given time is basically a current, right? So from the good battery, there is energy that is getting transferred to your weak battery. Okay. And keep in mind, there should always be a return current path. So whenever you draw, the reason I'm showing this is because whenever you draw a circuit, it is not only that the current is flowing in one direction, you need to have a return current flowing back, same magnitude of current flowing back in opposite direction. This is how electrical circuits are represented. If you remove this as an example, if you connect only this and then you remove this one, right? Let's say you don't show this, then the circuit is incomplete. So are you clear? So basically the way to represent a circuit is not only you're showing the forward current path, but you should close the loop. So current goes from here, it charges your battery, there is an ionization that happens, then the current should flow back from your negative onto the positive side. So the loop is complete. Every circuit that you build and you analyze, you have to close the current loop. Right? Fundamental principle of circuit analysis. If you don't close your current loop, then you fundamentally you violate the basic, you'll be violating basic principles. Okay. So keep in mind, always, even if you show that, okay, it's the good battery that is doing something to weak battery. So you might think that only this thing is happening or forward side is happening, but your electrical circuit is only complete when you also indicate the return current. This is the return current. So whatever weak battery is taking, it will return back through the other terminal. Clear? And this you need, and I'm showing this example to indicate the importance of closing the current loop. Clear? Any questions on this?
I have
Every
a
circuit.
question.
Yeah.
I have a question that is unrelated to this part. Actually, in antennas, we don't see a complete circuit. It is just a single line. So how is that working?
You mean antenna?
Yes, sir.
So that's your RF energy, right? See, it is, there the antenna assumes that your earth is a big ground. See, what you are showing is you have an electromagnetic wave that comes in, but the electromagnetic wave or your EM waves are now getting generated also with some circuit which basically has a global ground, right? When what is hidden there is, there the return path is through ground, which you don't see it. But everywhere, this is a rule, fundamental rule, that there is always a return path. It's never a one-way traffic. Okay, and only then will the circuit gets complete. Okay, clear? And this is how you should always think. There is always a return path. Whatever you supply energy, or especially in terms of current, there will be a return path always through your ground. Sometimes it is not obvious, but there is always a return path. Okay. All right. So with that basic principle, let's move on and let's look into fundamental voltage and current representations. Right. Okay. Left side, there is a circuit, and we can show that the current is flowing from left to right, and we give a magnitude of this current. We say, okay, my current is flowing and I have 2 amperes of current, 2A, that's flowing from left to right. Okay. And whenever the current is flowing from right to left, right, you can also say it is, let's say in this case, you can say that it is right to left. This is 3 amperes as an example, from right to left, or you can also say this is minus 3 amperes from left to right. Okay, common convention, very simple thing. No, a minus simply tells us that it's an opposite direction. That's all. Even though the arrow is in the same direction as circuit 1, a minus 3 ampere here simply means that in reality the current is in opposite direction. The positive current is in opposite direction. It is indicated as minus to show it in opposite direction. That's all. Right? Do you really have a negative current? No. Is there a negative? So and again, keep in mind, your current can be negative your voltage can be negative. Your power is always positive. Voltage into current. Power is not a vector. Power is a scalar. So whenever see power is a fundamental property. Power is always real. Power is always positive. There is nothing like a negative power. Okay, so whether you are delivering the power or again the same thing here. Whether if you can use a convention to say if I'm delivering the power, then it is a positive quantity. If I'm absorbing the power, then it's a negative quantity, right? But in reality, keep in mind, fundamentally, all these quantities are real positive quantities only. You use a minus sign to indicate an opposite direction or indicate a different property. In one case, it is absorbed. Let's say energy is absorbed or energy is supplied. To indicate whether you are absorbing energy or supplying energy, you use a negative symbol. But in reality, it just means that you are changing the property. But otherwise, it is either a left to right or right to right. So the negative is only a change of direction. That's the point. Okay. So similarly, a voltage to current relation, right? If you see here, the first thing, so you have a circuit. So this is your circuit, and the box you see here is an element. Okay. You can call it as an element, or you can call it as a load. Right. Now, whenever you have the circuit, in this case, let's say the circuit has terminals which has 3 volts across the terminal. So a plus minus simply means that VA, so voltage on node A minus voltage on node B is equal to 3 volt. So whenever we show a convention that says, okay, A is plus and this is minus, and then you put 3 volts right across this, it just means that the difference between the two voltage terminals VA minus VB is 3 volts. Is this clear? Remember this convention. It just because and why should we do VA minus VB? Because A is plus and B is minus. So A is the higher terminal and B is the lower terminal. So higher terminal minus lower terminal is 3 volts. Okay, this is the convention. Now from A, I show a current that is going out of A with a positive quantity. I current is equal to 2 ampere that goes into E, and whenever 2 ampere goes into E, so if A is giving out 2 ampere, B should take back 2 ampere, right? This is the rule. It should take back 2 ampere. Whatever happens here, it doesn't matter. But from the circuit perspective, if it is giving out something, it should get back the same thing. Okay. So whenever we see that there is a current entering the element, so when I say the element, this is the load. So it is not, so the gray area is a circuit, or you can call it as it's a circuit, or you can call it as a source. But the element here E is the dabba, the square dabba that I've drawn here. Okay. When the current enters E, right, you're giving, or in this case, think of that battery, car battery. You are charging E. Okay. So when you're charging E, this means energy is being absorbed by E, right? Whereas when you draw in other direction, same voltage, A and B is still the same, which means VA minus VB is exactly again 3 volt. However, the element is now supplying current into A. So the current is going into A and coming out of B. On the top diagram, current is coming out of A and going back into B, whereas in B, current is going into A, right? Here, which is the main battery, which is the good battery? In the bottom side, which is the good battery? Is this a circuit or is this the element? In the bottom B diagram. Yes?
D.
E
VB
element,
minus
right?
V.
Yes. So no, VB minus V, VA minus VB is 3 volt. This is 3 volt only. There is no confusion. It is just that the element is now supplying energy to circuit. Yeah. So element is your good battery, circuit is your bad battery, weak battery. Okay. On the top case, A, element is your weak battery and circuit is a good battery, because good battery is now supplying current into E. Okay, the reason why I put good battery, bad battery is to understand which is charging what, where is the energy transfer happening. Okay, just to keep you understand. But in both cases, VA minus VB is 3 volt only. There should not be any confusion. VA minus VB is 3 volt in both cases. The difference here is that in one case, energy is absorbed by the element in the top case, and in the bottom case, energy is supplied by the element. Okay, so whenever you want to think of this, right, go back to your good battery, bad battery case. Who is charging whom? Okay, and then you will know, okay, is the energy being absorbed or energy is supplied? Okay, now let's look at some basic voltage representations here. Okay, so the third side, the circuit 1, here I show V1 as 2 volts. What does this mean? Mathematically, what does this mean?
VA minus VB equal to
VA, very good. VA minus VB is equal to 2 volt, right? And why should I put A minus B and not B minus A? Because A is shown as positive and B is shown as negative, and so it is always higher voltage when I show it in this representation. It is always higher voltage minus lower voltage. So VA minus VB is 2 volts, right? So from the diagram, you should be able to write a mathematical representation, or from a mathematical representation, you should be able to draw the diagram clearly. Okay, it should work both ways. This should be simple. And see, all these might sound very elementary, and then, but believe me, as we build on this, right, these fundamentals really help you to start solving circuits. Okay, right now it might seem ki are ye to fundamental, ye to mujhe pata hai, but then you'll realize that if this part is confusing, right, then it just adds up more confusion a little later. Okay, same thing. The second circuit, look at B. It says V2 is minus 5 volt. How do I write the mathematical expression?
VB minus VA.
VB minus VA.
equal minus 5 volts.
Yes?
VA minus VB equal minus 5 volts.
Good, very good. Let's always start with this. VA minus VB is equal to minus 5 volts. Okay, do not start with VB minus VA. Okay, ultimately it is the same. I mean, it is same, whatever you're saying, exactly same. VB minus VA is 5 volt only. Understood. But when you write the mathematical expression, start with positive. Whatever is the positive sign, whatever is your negative sign, VA minus VB is whatever the value that is given. That's it. You start with this. Eventually, mathematically, you will see now, okay, this means it's nothing but VB minus VA is equal to 5 volt only. So it is right. But when you start writing the math equation, right, stick to your fundamentals. Positive minus negative is your voltage. Okay, now same thing. Let's write down the second equation. Third, for C, how do you write the math?
VB minus VA equal 5 volts.
VB minus VA.
VB minus VA is equal to
5 volts.
5 volt, right? Again, what is the rule? We started with the positive terminal. Whatever is the terminal, VB, negative terminal, minus VA, and whatever is the magnitude, VA. So effectively, B is same as C. You agree?
Yes, sir.
B and C are same. I'm just representing, either I put A as negative and write it as plus 5 volts, or A is positive and write the difference as minus 5 volts. Both circuit 1 and circuit 2 are exactly same. So do you agree? Agree with this?
Yes, sir.
Yes.
Clear? So
Yes.
rule, start with positive terminal. Thumb rule is start with positive terminal VA, then negative terminal VB, and whatever is the voltage given, write that as your math equation. Oh, positive ho sakta hai, negative ho sakta hai, doesn't matter. Right? Then you simplify it. First, representing mathematically, you should be very consistent, and having one consistent rule, right, helps you to be very clear in your math. You will never make mistakes if you just go with one simple rule. Okay, these are voltage representations. Let's move on. Okay, so a fun game. So how does voltage is add? Right? So we all know, we all played snakes and ladders game, right? You know, when you throw a dice, what happens? Whenever you get a ladder, you go up and you now move on, and whenever you get a snake, right, you come down to some value. Okay, so a ladder is a positive voltage source, and a snake is a negative voltage source. Right? If you have to reach from 1 to 36, right, you need to make sure that ultimately, even if you are coming back to a snake, you climb a ladder again, go to the top, and keep adding everything and so on. And when you're playing this as an example, is this going in series or is this a parallel? Are you going in a series or are you doing some parallel stuff here?
Series.
Snake and ladder game. It's a series. It's a series thing because you have a ladder, and let's say you go to a certain number, you throw a dice, you add that to the previous number, right? And then suddenly you see a snake, you go down. So you're basically subtracting that number, you start again, right? It is a series configuration, nothing else. So you're adding, so you're basically adding plus, you're adding another plus, then you add a minus whenever you get a snake, go back, and then so on. And finally, ultimately, to reach 36 number, you have to keep adding and so on. So voltage addition is basically a snake and ladder game. You have to add voltages only and only in series. Voltages always adds in series, right? Okay, so now for the quick range, let's say I connect. Let's give a small food for thought, right? Practical problems. Now, voltages we said should always be connected in series. Okay. What happens when I connect voltages in parallel? Let's say this is voltages I connect in parallel. Two terminals. Huh?
Both voltages same, sir.
No, I take two source meters. One has 2 volts output, other has 1 volt output, right? I will short both of them. And this happens, if you have spent time in your lab, right? Every one of us would have connected source meters in this way. Guarantee. I did it many times. No, by mistake, I did it many times. And each one of us in your labs would have connected voltage sources in series. Okay, so we said voltage add in series, that's fine. But what happens when you connect in parallel? So who wants to answer this? Is it 2 volt? Is it 1 volt? Or is it what? 1.5 volt? Is it 0? Is it what is it what happens when you connect 2 volt in series? A classic interview question. Classic interview question. This is basically where your fundamentals are tested. Do you understand voltage source correctly? This is where people test you. Okay, classic interview question. Who wants to give it a shot? It's okay. I mean, give it a shot. Try it. Think aloud. That's okay. You may be wrong, or you may be right. No problem. But let's just understand. Let's debate. Let's understand.
V2 minus V1 divided by
V2 minus V1 divided by. Okay. That's sounding very complex math, right? No. So, okay. So if you have to solve this equation, right?
Voltage will be dividend.
Voltage will be
Dividend. I mean,
divided. Okay. Bring it on. What else? What other possibilities? You will not see this in textbook, I guarantee.
Yes, sir.
Nobody is asking you this question, right? Unfortunately, nobody is asking you this question.
Because these voltages are the independent sources.
Yes. So what will be the V out?
V out will be Not defined.
Okay, it is not defined. So you have a 2 volt or you have 1 volt. See, something should happen, right? It cannot be undefined. Cannot be undefined. Something should happen here. Okay. So the way to understand this is you have two brothers who are playing, what do you call it? This game. क्या बोलते हैं उसको?
Arm wrestling.
Arm wrestling. Fantastic. Thank you, Shiva. Playing arm wrestling. Okay, who will win?
Stronger.
Who has more
Stronger
energy?
Stronger, more energy, more powerful.
Yeah.
He will somehow bend the other one, right? Okay. So who is stronger here?
2
2
volt.
volts, of course.
2 volts.
2 volts is stronger. So, but then electrically something should happen, right? And electrically, I mean, 1 volt is connected to V out, so I should see 1 volt. So what is happening to this 1 volt? Right? Something should happen to 1 volt. Okay, 2 volt is dominant, 2 volt is more powerful.
I think the voltage will drawn from highest energy to lowest energy.
Sir, if we are having multiple paths between V in and V out, then the current is always 0, sir.
Will that act as a open circuit and we get only output as a 2 volt? Is there a possibility in that way?
It's not an open circuit.
So these two are ideal, right? Like if in practical, there will be an RS as well.
Very good. Very good. Okay. If you have, okay, in other words, if you have ideal voltage sources, right? If you have ideal voltage sources and you short both of them, you will see a spark and it will burn these wires. It'll just burn the wire. You'll see a spark. Why? That is because when you build this model, right? Think of it. What is a wire? Wire is a resistor. You can now think of this wire as a resistor whose value is very, very small. Milliohms. Maybe milliohms.
Okay.
Right? Fair enough?
Yes, sir.
Okay. Now, easy. I have 2 volt here. I have 1 volt here on this right side. Now, what is the current I'll see in my wire?
2 amps. Sorry.
Sure, it is 2 amps.
Yeah.
2 minus 1 divided by
R.
0.
1 milliohm.
Milliohm. Yeah.
How much is the value?
1 kilo.
Unit. Volt by ohms is how much?
Amps.
How many amps?
1000.
1000 amp.
1 volt by 1 milliampere. Sorry, 1 milliohm. I'm sorry. So this is 1000 amperes. Okay. If you connect this, what happens is wire. I mean, this is basically, a small copper wire or something, right? If you do this, what happens? Katak. 1000 amperes will flow instantaneously. It'll spark and it'll just break. Circuit will break. Okay. So first of all, V out, what happens is that, V out, it depends on where the circuit will break. As an example, if the circuit gets burnt here, right, your V out will be 2 volt. If the circuit gets burnt here, then you disconnect the 2 volt and then you're seeing maybe only 1 volt. Right? It can happen anywhere. If the circuit gets broken, it will not get broken here, V out, because current won't flow here. But ideal voltage sources, the circuit will break. Okay. Now let's talk about practical. So who was the one who mentioned about RS?
Bharat.
It is OB, right? Bharat. Hi, Bharat. So good. So now let's talk about practical circuit. So ideal is clear, right? I can think of a wire as a very, very small ohmic resistance. So the moment I connect something, I get a spark and it will burn. So it's the same thing. Think of two batteries, a positive and negative terminal with slightly different voltages. Bring both batteries, touch both the batteries. What will happen? It will spike. You'll see a quick discharge, zing, and then it just damages or it just leaks the whole battery when you short two voltage sources. Practically, what happens? Okay, this is ideal scenario. Okay, when you assume that there is a zero impedance or very, very small impedance. Practically, what happens is that each of these voltage source or source meters have a output impedance. Okay, so the way the instruments are built is that these instruments are not. So for example, now we mathematically calculate that this is 1000 amperes, right? Can the 2-volt source meter really give 1000 amperes? Can it really give 1000 amperes? No, impractical, right? No instrument can source 1000 amperes here. So, and that is because practically every element will have a series resistance, RS. And this series resistance tells us what is the maximum current that this voltage source or source meter can deliver. Example, if you had a 2-volt source, okay, and you have a series element RS. So this is what you are basically seeing. The source meter output is this. Okay, this is your instrument. This is what goes out. This is your ground. Right? Now, if you suddenly short this to ground, right? Many times this happens. Like, you know, you take the wire and somehow connect it on the breadboard to your ground. Right? This would have happened to all of us. You know, it was 2-volt. By mistake, you've just connected it to ground. You shorted on the breadboard. So this means you are directly connecting it back here. Right? What is the maximum current that this can supply? What is the max? 2-volt divided by RS I max. So is this clear? Is this clear to everyone?
Yes, sir.
What an internal impedance of a voltage source tells you is the maximum amount of current that it can deliver at any point of time. Whatever be the circuit, the maximum that it can do is 2-volt by RS only. If you pick RS as, let's say, 10 ohms, right? 2-volt by 10 ohms is simply 200 milliampere. Okay, under any circumstances, your current cannot exceed 200 milliampere. If RS was 1 ohms, it will supply 2-volt by 1 ohm, which is 2 ampere current. So when you source meter, when you turn on the knob, right, you're setting the current setting of this. Now for the source meter, this is exactly what you're doing. You are changing the internal impedance of the source meter. Whenever you go to a 2 ampere setting or 200 ampere setting, you are changing the internal impedance. Is this clear?
Yes,
Practically every voltage source will have a series resistance. In this, ideally you want the series resistance to be as small as possible, right? Ideally RS equal to 0, and this means that, you know, your voltage source should be able to supply infinite current. RS 0, this means you can supply infinite current, but practically there will always be an RS because instruments cannot supply infinite current, and RS is defined by the maximum current the voltage source can supply. Okay, now with this understanding, let's say you had RS1 and you had RS2 for this voltmeter. Now tell me, what will be your Vout? Your Vout is going to be approximately, you know, depending on RS1 and RS2, anyway between 2-volt to 1-volt. I mean, if your RS1 is small and RS2 is a bit large, then you will be closer to 2 volts. Now 2-volt will supply the current. So this is the energy is supplied by the 2 volts and energy is absorbed by the 1 volt. Clear? In this case, when you connect voltage source in series, right? Even though it's a voltage source meter, it is not sourcing current, it is actually sinking current. This means it's absorbing energy. And where does the energy come from? It comes from the 2 volts. Okay, and what is now the total current? The total current is 2 volt minus 1 volt. The total current that this can deliver is 2 volt. This side 2 volt, and you have 1 volt here, right? 2 volt minus 1 volt divided by RS1 plus RS2. So series resistance always. So whenever, so what is a series resistance? If the same current flows through the resistor, then it is a series resistor. You can add them. Okay, so this is the maximum current that is flowing through it, and this is the current that is supplied by 2 volts, and this is the current that is absorbed by 1 volt. Energy is supplied, energy is absorbed. So normally you don't connect 2 voltages in series because of this reasons. You really don't know internal impedance. You can be 2 volts or you can be 1 volt. You may be between 2 volts and between 1 volt. Clear?
So one doubt here, that car battery which we asked, right? So that case, how we are connecting the one?
Same thing happens. You have it's the same thing. A car battery is a voltage source plus impedance, internal impedance. This is how a car battery is modeled. It's exactly same as this. You have a voltage source and you have a series. When a car battery is weak, the voltage source is smaller value. The value of this is small. Typically a lithium ion battery, a fully charged lithium ion battery is 4.2 volt. Right? A fully discharged lithium ion battery can be anywhere between 1.8 to 2 volt. Right? So this actually means that your strong battery has 4.2 volt. Your weak battery will have roughly 1.8 volt. Right? So of course, there is a voltage difference. You will now transfer energy. You will transfer energy across this. That's all.
So, but the arcing we don't see because of these ratings are less.
So arcing you will see sometimes when typically there is a sequence where you connect and disconnect your resistors, right? I think you typically don't want to touch your positive terminal. So I think you connect your grounds first, and then you connect your positive terminal. So there's a sequence to avoid arcing. Okay. And similarly, while disconnection, you do in an opposite way. Okay. You disconnect positive first, and then disconnect negative later. Okay. So it's vice versa. So is it clear? It looks very. I mean, these concepts look very simple. Voltage source, big deal. But the concept of voltage source should be very clear. Practical voltage sources always come with series impedance. Okay, and these are, what I'm talking here are classic interview questions. People will challenge you about your knowledge of basic voltage sources by asking these questions. Okay, do you understand what happens if you connect 2 voltage sources in parallel, or what happens? Either 2 volts, either 1 volt, something, right? But this is what happens practically. Now, what about current flow? Current flow is like river. It's like a river flow. A river flow splitting into tributaries, which means, this is our classic, if you look at Ganga river, right? River Ganga flows. You have Ganga river coming in, and a lot of small currents, small tributaries come, join, they become a big river. Okay. And then slowly some more water comes in, big river, and then it splits into more tributaries, and then finally something goes and joins your sea. Okay. Think of a current flow exactly like a river path. So everything comes, joins, flows together, and then distributes back. Okay. So current sources always add in parallel. This is a parallel connection. Saath mein ja rahe hain. Okay. This water and that water, everything joining together, going as one big river, going somewhere, and then they distribute. Okay. Becomes another tributary. This becomes another tributary. The classic case of this is human blood flow, right? How does it even, in fact, a good example of why the return current path is important. See, the way God has built us is your arteries are pumping blood from your heart, and it's not a one-way path, right? Arteries pump the blood, the impure blood comes back as return path through veins. अब सोचिए, you didn't have return path, you didn't have veins at all built, right? सीधे से जाएगा वही रुक जाएगा, right? There is no return path, correct? So even the way human body is built is anything that goes back somehow should come back, pure or impure, वो आना चाहिए. So water flows, then comes back. You can say, अच्छा, glacier से water आ रहा है, it's going into this. Where is the return path, right? Return path comes through, natural cycle, environment. You can moisture again back, all of this. Energy, again, fundamental principle. Energy can either be created or destroyed by changes form. Okay. So point here is current flow is like a river splitting into tributaries. So currents always adds in parallel. Keep this in mind. Voltages adds in series, current adds in parallel, adds or subtracts in parallel. Okay, same logic, same equation. What happens when you connect current sources in series? Same logic. You are not supposed to connect current sources in series, right? It comes in parallel. Now let's understand what happens when you connect your current source in parallel. Okay, apply the same logic. What happens? Arm wrestling. Karo.
Depend on parallel source resistance.
Okay, practical current sources have some parallel resistance. It's called as a shunt. Anything that comes in parallel is called as a shunt. Okay, so you're directly jumping ahead. So let's connect. Then practical sources, you have a resistor. Okay, this is I1, and let me call this as I2. Okay, and this is R1 or R shunt 1, and this is R2. Okay. Now tell me, what happens when I connect current sources in series? Arm wrestling. When I1 equal to I2, let's say this is VDD. Okay. Now case 1, let's discuss about this. Case 1, when I1 equal to I2, then V out is equal to how much?
R2 into I1.
I1 equal to I2, same source. I1 equal to I2, this means R1 equal to also equal to R2.
R into I1.
Exactly matched sources, exactly matched. I1 equal to I2, R1 equal to R2. What is V out?
R square.
R square.
R equal to IR, sir.
No, think and answer. See, it's a voltage. Finally, it's a voltage. The dimension should be of your voltage, I into R, right? Some I into some R. It's a voltage. Yeah, dimensions ka dhyan rakhna. No, don't just say IR
Sir,
square or
I effective into R effective.
What is I effective?
The addition or the product of I or R.
I1 equal to I2.
Just
that is the easiest question, right? So let's say I2 I write as I1.
I2 into R2.
And this is R1, right? Both are same. My thing is I1 equal to I2, R1 equal to R2. So I can just say I1 R1, I1 R1, right? So what is my V out now?
I1 into R1.
I1 R1.
Okay, what is my voltage? Two things that are exactly same from VDD to ground. I am asking about the midpoint.
Oh, VDD by 2. VDD by 2.
Sir,
VDD by 2.
I1 R1.
Do you agree this will be VDD by 2? Whatever it is, I1 R1 kuch bhi ho jaye, right? Anything, right? Ultimately, if this is the exactly same steady state, you should reach midpoint because everything is same. Whatever is the top, that's the same thing as bottom. Do you agree that if they were exactly balanced,
Yes, sir.
No mismatch, R1 is exactly same as R2, I1 is exactly same as R1, output should be VDD by 2. So how many of you don't agree with this?
Sir, it's just like mean point.
Mean, that's it. Two matched elements which are on should settle to midpoint, nothing else, right? Should settle to midpoint. You can calculate I1 R1, ultimately you should see the same thing. See, it's like saying you have a resistor. So I can redraw this and say this is I1 and I'm connecting I1 here. And by the way, I also have R1, right? So this will set the point. This VDD and this because this R is same, R and R, this should be VDD by 2. And the current sources will see VDD by 2 drop across them. The current sources will see VDD by 2 across. That's it. So the midpoint should be VDD by 2 only. Now the next interesting question is, what happens when I1 is greater than R1? I1 is greater than I2. is I1. Let me draw again. I2, R1, R2 is VO. So case B, I1 is greater than I2.
I1 or what? Yeah.
What is the, so
VDD
whenever,
VDD
go ahead.
minus VDD minus I1 R1.
VDD minus
I1 R1.
I1 R1 is your VO.
Yes, sir. Yeah.
Okay. Okay. Let's make it a bit more interesting. And I want to now color. Okay. For a minute, ignore R2, R1 in here. Let's talk about ideal elements, right? I have I1 on the top and I2 on the top, and I have connected. This is again a current source. Two ideal current sources which are somehow connected in series. So what will happen? Arm wrestling will happen, right? So if I1 is greater than I2, what happens to VO?
I1
R1. It's just greater.
For a minute, there is no R1, there is no R1, there is no R2, right? Ideal sources. So very high output impedance. So R1 and R2 are infinity for an ideal current source. Okay?
I1 minus I2.
It will violate your Kirchhoff current law, right? If you say I1 minus I2, right? Something gets violated. So
I1 plus I2, sir.
I1
plus I2.
I1 plus I2.
Yes, sir.
So the total current in the path will be I1 plus I2. You sure? Because current from supply itself is I1, right? VDD is giving you only I1.
I will
Can you
equal
get
to I2.
Yeah, that is your first case. I'm saying I have by mistake I've connected two source meters, I mean current source in series. Different values. I've set different values and suddenly I've connected.
I/2, I1/2.
No, not I1 by 2 because it is in series.
Sir, I1 plus I2 whole times VDD by 2.
I1 plus I2
whole times VDD by 2.
I1 plus I2 whole multiplied VD by 2. What is the dimension of that value? That is the power, correct?
Yes.
Okay, so I'm asking about the current flow. If you have I1 on top, I2 on the top, finally you should have one. See, as per Kirchhoff's current law, you should have only one current flowing from top to bottom, right?
It will be I1 only, it will force its way through I2.
Okay, and you're partly right. What it will do is I1 being the strongest thing, okay, will pull VO close to ground, close to supply. This will now go towards supply. Okay, and now I1 will stop working as current source and it will supply only I2 because bottom side you can only accept I2. Strange thing with current sources. You try this experiment. First I1 will pull it up to VDD. Okay, it will reach a point where it will go beyond the compliance, the voltage compliance of this current source. It'll actually, the voltage becomes so high that it will break I1. I1 current source will break and stop working as a current source. And now it becomes almost like a voltage source with an impedance. And now because bottom side you can sink only I2, you will start effectively sinking only I2 current. Very strange and interesting experiment. You can try it out. If I2 was greater than I1, same thing will happen. Output goes to ground. The voltage becomes so low that the current source loses its compliance. I2 loses its compliance. I mean, for any, see, remember, any current source to operate, right? You need a voltage compliance, which means you need a certain voltage across the circuit to make it act like a current source practically. That's basically is called as a compliance. So how do I think of compliance, right? If I have this is my current source as an example, okay, and this is my VO across the current source. Let's say this is my current source, I out. Then this is my VO across my current source, I out. Okay. What happens normally with these current sources is that until VO reaches a certain value, in this case, until VO reaches a certain value, right, the current will slowly go up, and beyond a certain value, it becomes constant. This is where normally you operate here. You operate to the right side of this. This is where your current meters actually operate, because your voltages are always large, and this is where you are acting exactly like current source, because it's a fixed constant output. So it is a flat line. In this case, your voltage will become so low that you start entering this region. You are now operating in this region. It's a false region of operation. You don't operate current sources here. Practically, you end up here, and because you end up here, it's no longer a fixed current source. It's now a variable current source, and whatever is the other current source value, right? It will go and settle there. Okay, could be a bit confusing right now, but just for now, just go with this assumption saying only finally one current will flow, which is the smaller of the both, but the voltage will be pulled towards the top side. And this is a good experiment to do in your lab, right? Whenever you do this, or even in simulations, you can try this in your simulation. Pick some simulator and you can try it. It will basically, the arm wrestling will happen. The stronger current source will pull it towards that. If the high side current source is stronger in magnitude, the output voltage will go up. If the bottom side current source will be strong, then it will keep pulling down. Right? That is what will happen. And even in practical circuits, when you replace this current source with MOSFETs, right, this is what happens. Let me just replace this current sources with, just for the, so exactly on this side, let's just replace this current source with MOSFET. Okay, I have PMOS on the top, I have NMOS on the bottom. Okay, now when I'm exactly balanced, right, my current in PMOS and NMOS are same, I should go, theoretically I should go to VDD by 2. Now when I increase my voltage, when the voltage input voltage goes up, what happens? The NMOS starts acting like a powerful current source now, because the VGS is larger. So this current source is now, the bottom side is stronger, right? What happens now? It will pull the output to close to ground. This is your inverter. This is exactly how an inverter operates, right? Voltage goes up, output voltage goes down, because the bottom current source is now stronger. It is pulling it. If your input goes low, right, then the top current source becomes stronger. This current source becomes stronger. PMOS current source becomes stronger, because you have larger VSG. Okay. Now it is stronger, so the voltage gets pulled up. Arm wrestling. No, PMOS is stronger, it will pull it up. This is exactly your inverter characteristics. V in, V out, goes down. This is your inverter characteristics, right? Simple. Smaller your V in, higher is your V out. As V in increases, V out drops down and then becomes 0. Two current sources fighting here, that's it. Two series current sources are fighting, nothing else. This is your inverter operation. This is nothing different from thing that you see. Two current sources at a certain voltage, one of them starts dominating, arm wrestling happens and it will pull at other direction. Okay? Clear what happens when you have two current sources? I mean, these are things that you see practically. And everywhere we see this, right? These are nothing but current sources in action. One of them comes out of being a current source now. Whichever has higher current, right? Just comes out of current source and becomes more a impedance, or it just becomes a resistor or an impedance. Then only the other one becomes or remains as a current source.
So this is a digital circuit, right? Which are like
yes. And if you look into, I mean, you can call it as an inverter, you can call it as a class B amplifier, you can call it as an analog amplifier. Everything is same. It's not a digital circuit. Which region of operating you're looking at? So this is a digital region. In this region, you're operating as a digital transistor, digital and digital. Okay. In the middle region, this is my analog regime. This is analog regime here. If I can bias it to be in this net, right? A small input voltage can give a large output voltage. So it's a gain amplifier. It's an amplifier. Same circuit based on where and how you're looking at it. It's the same thing. It's still an inverter, but don't assume that a PMOS on top and NMOS on bottom is not. It's an inverter for sure, but it's not necessarily a digital circuit, right? This is it's an amplifier. It's a classic amplifier. And because in that region of operation, if you can somehow maintain your DC bias to be here, right, you get a very high gain. A small change in V in can actually give you a large change in V out. So it's a gain. It's an amplifier. It's a good small signal amplifier. Okay, and the inverter operation is nothing but this. You have two current sources fighting for each other, fighting for control. Whichever current source is stronger will pull the other one. That's it. Clear? Okay, so bottom line, voltage sources add in series. Keep this in mind. Very important. And current sources add in parallel. Okay. I know we spent a lot of time on this class. But I think it is important because like I said, we are talking about fundamentals. We are talking about how clear are we on the basic concepts of voltage source and current sources, right? Probably a bit too early for assignment, but then let me upload them. However, I'll upload them, and then the continuation of this we will talk about in the Thursday class. Let me just leave it with a quick example of power so that you can start attempting the assignment. Okay. Power is nothing but voltage into current. Okay, I'll introduce the concept of power and then we'll stop here. Okay. Power is nothing but voltage into current. Now, if voltage is function of time and if current is a function of time, then your power can also be written as V of t into I of t, whatever that value is, right? Okay, and now you can do all the mathematical process. You can take an average power, which means over a period of time, what is my power, the total amount that you are taking out from battery. What is your average power consumption across the time? So you take an average across this. It is an average of all the instantaneous V of t into I of t. Multiply at different points, multiply all of that. Now you take an average. That is your average power consumption. But ultimately, power is voltage into current. Okay. If somebody asks you to accurately calculate if this is a V of t, right? Is your power same as V average dot I average or V of t dot I of t whole average? So can I say power is okay? What is my question? I have a current that is changing with time, and I have also some voltage that is changing with time, right? Should I take average current? So just average the current waveform, average the voltage waveform, and multiply the average. Or should I take voltage, instantaneous voltage multiplied by instantaneous current and then take my average of V dot I, which gives me the accurate result. Both are close. I'm not saying one is different, but which is the most accurate way of doing it? And the answer to this, option A.
Yes.
I believe the latter one.
Yeah. So the better or the more accurate way of doing this is second option. Okay. But keep in mind, if the variance, okay, here the assumption is that the change in current or change in voltage is reasonably small when compared to the overall average mean value. So this means if you had 600 millivolt and then you had 10 millivolts plus minus something, right? Then the change or the variation is smaller than your mean. Okay, so if the variation is smaller, then whether you do in the first case or you do in the second case, approximately the answer is same. It will be no different. But if the variation is large when compared to mean, then the second one will give you more accurate result. The average power is instantaneous power, P of T. You take the average of that term. Okay, so the thumb rule is whichever value you want to calculate average power means write down the power equation. So it is V of T into I of T, then take your average. Okay, that is more accurate. However, if the variation is small, if the peak to peak is small, right, both V average dot I average will give you almost the same result as V dot I whole average. But the most accurate way of representing is taking the power and then doing it. Okay, and this is also better because sometimes your current can go to zero in some instance and voltage can go to zero some other instance, especially power converters. You see this classic problem there. So better to always have V dot T into I dot T and then take your average. Okay. So last minute, one more minute on this. Let's just take the example. The first element, tell me, so this is your circuit, okay, and the dabba is your element. Okay, now which is absorbing power and which is supplying power? The gray is circuit, dabba is your element E. Okay, first case, A.
Both figures A is
A is
both figure A, sir.
both are absorbing, and downwards A is
No, let's just
E is
focus on the first
delivering.
one. First
The-
one.
absorbing.
What is absorbing?
Element
Yes,
is
sir.
absorbing.
Element is absorbing.
Yeah.
Okay. If I just draw this ulta, right? So look into the current. Current is going from negative into E, but then it is coming out of E on the positive side. When a positive terminal is sending current out, right?
Delivering.
It is delivering. Okay, just the way it is drawn, don't get confused.
Okay.
So it is same as the same thing, remember the good battery? The good battery has positive terminal and the current is coming out of that positive terminal, right? So is it clear? Kavya, is it clear?
Yes, sir. Yes, sir. It's supply.
Yeah, so it's drawn this way, but don't get confused. Don't get confused. It is current going here and current coming out. So whichever positive terminal you see the current coming out, again, that's the good battery. That is supplying the power. Okay, and the circuit is absorbing the power because it is going into the positive terminal of the battery. So this is the good battery, this is the bad battery. No. B, second one. Tell me which is the good battery, which is the bad battery, which is supplying, which is absorbing.
Circuit is supplying, element.
Very good. Circuit is supplying because the positive is now charging. So good battery is circuit. That is supplying your bad battery, which is your element. Okay. Now, same thing. What about the bottom?
Element is supplying.
Element
Right.
circuit is absorbing.
Why? Why is element supplying? Because the current is in this direction. So this means the current is coming out of the positive terminal of E. So E is the good battery.
Yeah.
Okay. So E is supplying the power and circuit is absorbing the power. It is getting charged. Okay. So always this good battery, bad battery, when you remember, right? It just helps you very easily to visualize. Now, whenever you are confused, right? Think of it. I have a good battery, bad battery. Okay, I'm supplying a current. So this is supplying energy. Keep this in mind. Similarly, what about B, the last one?
Circuit is Supplying and E is absorbing.
Very good. Circuit is supplying the power because the current is in this direction. Okay, it is getting into E and so on. So just the way it is represented, you can now distinguish between who is supplying power and who is absorbing power. Okay. Good. So now this is all your, so I'll upload this. This is your part of your exercise. Okay. Determine the unknown variables. So power, you know, is voltage into current, right? Determine the unknown variables. What is your V? And then also identify which one is supplying and which one is absorbing. So I will upload this PPT. You can try it out. Okay. Similarly, there are, I'll talk about, let's keep this IV characteristics here. Okay, so we'll discuss this. We'll discuss this on Thursday. Don't want to rush through this, right? Okay. So, but now, I mean, we are slowly introducing now a bit of a math. Started slowly getting into this with some fundamental concepts of circuits and voltages, right? Now, and there are more. I will upload this entire slide set. The second half of the slide set we will discuss on Thursday. But you can start attempting. There are many problems in this slide set. So start attempting so draw the circuit. Start attempting this, okay, unknown variables, and start doing this. And we'll discuss more on Thursday's lecture. Okay, so just want to spend 2 minutes on now quick feedback. I know we are a bit late. Don't want to hold on over, but let's just stop sharing it. Stop recording.